Hey guys, I'm going to demonstrate for you our moment of inertia demonstrator, and to help review that concept and let you make some predictions about what's going to happen when we make some changes to this thing. And also we're going to use some data that we get from this to do a little mini lab to run through a calculation. So I should show this thing to you first. The way it works is this wheel on the front has a stack of pulleys which are different diameters. So we can hang a weight from them from a string and it will provide different torques because the diameter of the pulleys is different. Now, we can also move these weights in and out. We're not going to do that today because it's important to keep it very closely balanced, and it just is too much of a hassle to get it balanced. So we're going to leave all these in the same location, and we're only going to change the where we wind the string. Okay, so the first thing we're going to do is I have 100 grams hanging from this string here. You can see it will start to unwind. So I have 100 grams hanging there, and we are going to let it unwind 6 full rotations because that's just kind of how it works out to be. And we want to see how long it takes to unwind six rotations. So the radius of the pulley is 4 centimeters, and we have 100 grams hanging from it. Now it's hard to see when it's gone around 6 times. So I will say start and go. And what I would like you to do is time it to see how long it takes to unwind 6 full rotations. Okay, so pause it if you need to get your stopwatch ready, and then start it again when you're ready. Okay, so here we go. I will say start and stop, and I'll say stop when it's gone 6 full rotations, and you just time it. So here we go. All right, ready, set, go. And stop. That's 6 rotations. Now, when I did this before, I got about 14 seconds for that. Now I'm going to wind it back up again. Now we're going to run it again. We have still 100 grams, but this time I put it on a smaller pulley. So this time the radius is only 2 centimeters, whereas it was 4 the first time we ran it. So again, I want you to make a prediction about how long it's going to take. And the prediction needs to be, is it going to be the same amount of time or a longer period of time or less time? So it's the same weight hanging from a shorter distance and everything else is kept the same. Okay, so make your prediction. You can time this if you wish, or just kind of keep an eye on it and see what it is. Again, I'll tell you 6 full rotations. So ready, set, go. Five. Stop. That's 6 rotations. Okay, so if it took more time, that meant that the acceleration was lower, meaning that less torque produces a smaller angular acceleration. That's what it is. Now I want to try one last thing here. We're going to wrap it around the small pulley again, 200 grams from it instead of 100 grams. So we are doubling the force. We are doubling the weight hanging off this thing. All right, so we have a pulley of 2 centimeters in radius instead of 4, which is what we had for the first run. And we have 200 grams hanging from it instead of 100 grams, which we had last time. So we have doubled the force, but we have cut the radius in half. And I want you to make a prediction again, and then we're going to time this and see how long it takes to go around 6 times. Okay, so make your prediction, pause it if you need to think about it a little bit. And here we go. So ready, set, go. and stop. That was 6 rotations. And what you probably saw was that it was pretty close to the same number. Now you probably got it slightly faster for the 200 grams than the 100 grams I did when I was getting ready for this. Now, if you notice that, it's because when we wrap the pulley around the string piles up on itself and it effectively makes the pulley a larger diameter. So we said it was 2 centimeters radius, but it was actually, practically speaking, a little bit more than that because the string was piled up on the string. Okay, now for the experiment that I want you to do, we want to use the data for the very first run. So the 4 centimeter radius with 100 grams hanging from it. And our goal is to figure out what is the rotational inertia of this apparatus. Okay, that's what we're trying to figure out. What is the I value? Capital I represents the rotational inertia or moment of inertia. We want to figure out what I is for this setup. Okay, so now let's run through that exercise. We'll call it a kind of a mini lab where we're trying to determine the moment of inertia or the rotational inertia of that rotating apparatus. And we had 6 revolutions in 14 seconds. Let's use those numbers. And the radius of the pulley that the weight was hanging from was 4 centimeters. Okay. Now, the way I'm going to run through this is I'm going to let you try to do it on your own as much as possible. To go through, I'm going to solve the whole problem. What I would like you to do is pause it, try to do it yourself, and then if you get stuck, watch. And I will try, and so you get unstuck, and then pause it again and continue on, because we want to make this as independent as possible. I will try to solve it in a logical order so that hopefully I'll be doing the steps in the same order that you are, and we'll go through. Okay, one thing I did leave out of this is that it was a 100 gram weight that was hanging from the pulley, so I should show that here. So 100 grams, which is 0.1 kilograms. So that's a useful one. Okay, now the equation that we're going to use, the concept we're going to use is this idea of torque being equal to I alpha. This is the rotational version of Newton's second law. Torque is also defined as Newton's times meters. And we can set these two terms equal to each other and get a useful equation. So I alpha is equal to Newton's times meters, the radius. And this particular problem is one where this version is useful to us. All right, so we're going to go through and we're going to see what information we have and what information we need to derive from the information that we do have. Now, I, we don't know. That's what we're trying to find. I should probably put that in here. Find I. That's our goal. We don't know I. We're trying to figure that out. So we need to know the angular acceleration. So that's probably a good place to start. We also are going to have to figure out newtons because all we have is the mass. So we'll have to do a step here. We have to figure out the newtons. And then the meters we already have. So let's start off with alpha here. So the information we're given is a number of revolutions and a time. So this is sort of like being given a distance and a time, and we're trying to figure out an acceleration. So if this was a linear problem and we said, hey, we want like 6 meters in 14 seconds, find the acceleration, we would use this equation here. D equals 1/2 AT squared. All right, so we have 6 revolutions. Well, if we're going to translate this into rotational terms, we're going to get theta is equal to 1/2 alpha t squared. That's the rotational equivalent of it. But this works for theta in radians. So we need to figure out how many radians 6 revolutions is. So we have 6 revolutions times 2 pi radians per revolution. And that is going to be the number of radians of rotations in this. All right, 1/2 is still 1/2. Alpha is what we're trying to find for this step. And then we're going to multiply that by 14 seconds quantity squared. All right. And when we do the math here, let's find a place with less glare. That looks like a good one. So we're going to do 6 times 2 times pi. So 37.7 radians. That's how many radians we went through, which seems reasonable because 6 times around and roughly 6 per. That's good. Times 2 and then divided by 14 squared comes out to be 0.385 radians per second squared. So 0.385 radians per second squared is our angular acceleration. Okay, so that's the first step. The second one we have is we have to figure out newtons. And as you know, force of gravity or weight is equal to mg. That's our standard weight equation. And that's going to be 0.1 kilograms times 9.8 meters per second squared, the acceleration due to gravity. And that gives us 0.98 newtons. That is the force. Okay. Now that force, that 0.98 newtons, is pulling down on the edge of a pulley, and the radius of that pulley was 4 centimeters. 4 centimeters, which equals 0.04 meters. And again, to make this work, we got to have meters. We can't just leave it in centimeters. All right. So we have enough to feed this now. So I alpha is equal to newtons times meters of torque. So I times 0.385 radians per second squared is equal to 0.98 newtons times 0.04 meters. Now we just solve for I. This will work. Let's see, we're going to do that one times 0.98 times 0.04, and we get I is equal to 0.102 kilogram meters squared, because that's the weird units that it comes out in. It might be worthwhile to check our units to make sure we're getting what we need. Okay, so let's do that. So we're getting I is equals to 0.98 kilogram meters per second squared. That's newtons, times 0.04 meters, because that's what we had. And now we're dividing this by 1 over 0.385 radians per second squared. Okay, so seconds squared cancel. Meters times meters makes meters squared, so that leaves us with kilogram meters squared for our units. And remember, radians is a dimensionless thing, so it just kind of falls away. What I would like you to do is make an image of the work that you did to solve this and attach it, okay? Show that you come down to this answer, 0.102 kilogram meters squared. And if it looks like you have the work and you came to the right answer, I'll give you full credit for this. It'll be a 10-point lab assignment, mini lab assignment. It'll go in your under the lab score. So again, hopefully this will be one where you can easily get a 10 out of a 10 on it. Okay. Please don't copy what I did. Try to do it yourself. Even if you watch what I did, then cover it up, start with a blank sheet of paper and work through it so you can see the process and how it works. The sticking points on it are going to radians here on theta. Also recognizing that this is the equation that you need to use, and then finding the radians. People forgetting to go to newtons is a common error, and people forgetting to go from centimeters to meters is also a common error. So try to catch all those things on your own. Show it to me, turn it in, we'll be good. All right, thanks for your time, and we will see you next time.